Hello, welcome if you're new, welcome back if you're not. My name is Talia. I'm an incoming fourth year student at UCSD studying chem and minoring in science education. This YouTube channel is an extra resource for anyone who is taking a chemistry class or just wants to learn some chemistry for fun. In this video, I'm going to be talking about doing equilibrium calculations, but with approximation, which is going to add an extra level of complexity to my previous video. So I hope that if you need some help with that concept, you will keep on watching. And without further ado, let's get started. We're going to start by doing a review of equilibrium problems and setting up ICE tables using this example problem. So I gave you a reaction and a K value, and we know that initially the concentration of NaCl is 1.50 molar, and your job is to determine the equilibrium concentration of each substance. So go ahead and give that a try. See if you can fill out the ICE table and set up the equation for K and maybe even calculate the equilibrium concentrations. Okay, so I filled out the ICE table based on the previous knowledge I have at this point and the concepts I went over in the previous video. So we know that the initial concentration of the products is going to be 0 because we were not told anything else. We didn't need to calculate Q. And we're going to be subtracting 2x from the NaCl because there's a coefficient of 2. And then by the same reasoning, we're going to add 2x to the NO and add x to the Cl2 because there's a 1 in front of the chlorine. And we are adding x because we don't know what the change is. So our equilibrium concentrations are 1.50 minus 2x, 2x, and x. And I wrote the K expression at the top for review. So now I'm going to try to put in all the information I have into the K expression. So our K value is 1.60 times 10 to the negative 5, it was given. And that is going to equal the concentration of Cl2, which is x, times 2x, the concentration of NO, squared over 1.50 minus 2x squared, because there's a 2 in front of the NaCl. Okay, so we obviously want to solve for x. The difference between this and the previous ICE tables that I've showed you is that now the denominator of this fraction is a quadratic. You can easily square 2x and you get 4x squared, but when you square 1.50 minus 2x, you're going to have to do the FOIL method, you're going to get 4 terms, and it's going to be a huge mess, and you're going to end up having to use the quadratic formula to solve for your equilibrium concentrations, which you can totally do if you want, but sometimes, I don't know, graphing calculators might not be allowed, and it's also just a lot quicker to not have to use it. You might be wondering, Talia, how can I avoid using the quadratic formula? And lucky for you, on the next slide, I'm going to explain it. So this is basically the setup we just had. I don't have the case set up here, but this is the ICE table. So to avoid the quadratic formula, when we have a really small k value, like the 1.6 times 10 to the negative 5, we can assume that the change in concentration of the reactants is so small that it is basically negligible or 0. And we know this because of way back when we did equilibrium concentrations, if K is less than 1, our reaction favors the reactants. If K is greater than 1, our reaction favors the products. So if K is less than 1 and is really, really, really small, the reactants are super duper favored. And not a lot is actually going to be subtracted from the reactants. So the approximation makes a little bit more sense in that case, because if our equilibrium is really favoring the reactants, this change is not going to be very large because the equilibrium isn't going to want to take away from the reactant side. So as a result, we would assume that this equilibrium rho is just going to be 1.50 instead of 1.5 minus 2x. Once we make this assumption, which I'll show you once we actually do the problem, we're also going to have to make sure the assumption is valid. So this only normally works if k is like 10 to the negative fourth or less, but we use the percent change formula in order to validate the assumption. And in order for the assumption to be valid, the answer that we get has to be, the percent change has to be less than or equal to 5%. So now you can see that once we make that assumption, the K formula is much more simplified, and we change the denominator to be 1.5 squared instead of 1.5 minus 2x squared. A note about the numerator, it stays the same. I just simplified what we had because 2x squared is 4x squared, and then multiplied by x becomes 4x cubed. So this is our new K expression, and now we need to solve for x, solve for the equilibrium concentrations, and check the validity of this assumption. So we're going to do that on the next slide. So now this is going to be using your algebra skills. We basically turned it into an ice table problem from previous videos. So I'm going to square 1.5 and then do some cross multiplication. Multiply that by 1.6 times 10 to the negative fifth. Divide by 4. And then I'm going to cube root that number. And using the correct number of sig figs, I'm going to get x equals 0.0208 molar. Okay, now we need the equilibrium concentrations. So I'm going to start with the concentration of NaCl. It's going to be 1.50 minus 2 times 0.0208. And remember to use the unrounded version in your calculator. And we're going to get 1.48 molar. The concentration of NO is going to be 2 times 0.0208, which is going to be 0.0416. And then finally, the concentration of Cl2 is going to be X, which is 0.0208 molar. All right, I'm going to highlight these answers. And now we're going to check the validity of our assumption. So if you recall back from a couple slides ago, the percent change is going to be the change over the initial times 100. We're going to look at the change column, which is 2 times 0.0208 over the initial, which is 1.50 times 100%. And we're trying to get this to be less than 5. And that equals 2.78%. So our assumption is valid. So this is a really great technique you can use when you have a really small K and you're noticing that you're going to have to solve the quadratic formula in order to get the equilibrium concentrations for the reactants and products in your reaction. I hope you learned something from this video on equilibrium calculations with approximation. I hope you'll join me back next time where I talk about KP. If you have any questions or comments, feel free to leave them in the comment section below, and I will do my best to answer them. I hope you enjoyed this video, and good luck learning chemistry.